The development of decision trees in the field of artificial intelligence has been a significant milestone in machine learning and data mining. In particular, the ID3 algorithm played a crucial role in laying the foundation for decision tree construction and paved the way for subsequent advancements. Here, we will explore the evolution of decision tree development from the ID3 algorithm, its limitations, and the subsequent improvements that have been made to address those limitations. ID3, Iterative Dichotomizer 3, was introduced by Ross Quinlan in 1986 as a method for constructing decision trees from labeled training data. The algorithm followed a top-down, greedy approach that recursively partitioned the training data based on the values of input features to maximize information gain. The primary objective of ID3 was to find the attribute that provided the most information about the target variable at each level of the tree. ID3 made several important contributions to decision tree learning. First, it introduced the concept of information gain, which quantified the reduction in entropy, a measure of impurity, when a dataset was split based on a particular attribute. By selecting attributes with the highest information gain, ID3 aimed to maximize the purity of the resulting subsets. Second, ID3 employed a recursive strategy to build the decision tree, expanding the tree from the root to the leaves in a depth-first manner. Despite its contributions, ID3 had a few limitations. One significant drawback was its bias towards attributes with many values. Since ID3 selected attributes based solely on information gain, it favored attributes with a large number of distinct values, often leading to overfitting. Moreover, ID3 did not handle missing values or continuous attributes efficiently. Another limitation was the tendency of ID3 to create deep trees, which could lead to overcomplex models that were prone to overfitting and difficult to interpret. To overcome these limitations, subsequent algorithms were developed based on the ID3 framework. One notable enhancement was the introduction of C4.5 by Quinlan in 1993. Which addressed some of the drawbacks of ID3 and introduced additional features. C4.5 extended ID3 by handling both continuous and discrete attributes, allowing for more flexible and robust decision trees. It introduced the concept of attribute-based splitting, which involved selecting a threshold value for continuous attributes to divide the data. Additionally, C4.5 introduced pruning techniques to avoid overfitting and reduce the complexity of the resulting trees. Pruning involved removing branches from the tree that did not significantly improve its accuracy. Another significant advancement in decision tree learning came with the development of CART, classification and regression trees, by Leo Brayman et al. In the 1980s. CART expanded the decision tree framework beyond classification tasks to include regression problems. Unlike ID3 and C4.5, which focused on categorical target variables, CART allowed for the prediction of continuous target variables by fitting regression models at each leaf node. CART employed a different splitting criterion known as the Gini impurity or the mean squared error, depending on the task. Furthermore, improvements in decision tree algorithms were made to handle missing values effectively. One approach was to assign missing values to the most frequent value or the value that minimized the impurity during the split. Another approach involved incorporating missing value indicators as a separate category during the splitting process. The development of ensemble methods also had a significant impact on decision tree learning. Bagging, bootstrap aggregating, and boosting were two widely adopted techniques that combined multiple decision trees to improve accuracy. Bagging involved training several decision trees on different bootstrap samples of the data, and combining their predictions through majority voting or averaging. Boosting, on the other hand, focused on iteratively constructing an ensemble of decision trees, by adapting the training data distribution to emphasize previously misclassified instances. Random forest, introduced by Leo Brayman in 2001, emerged as a powerful ensemble method that utilized the strengths of decision trees while reducing overfitting. Random forest combined the ideas of bagging and random feature selection. It trained a large number of decision trees on bootstrapped samples and made each tree splits based on a random subset of features. By averaging the predictions of these trees, random forest reduced variance and improved generalization performance. In recent years, further advancements have been made in decision tree learning. Gradient boosting, exemplified by the XGBoost and LightGBM algorithms, has gained prominence. These methods leverage gradient optimization techniques to construct decision trees that minimize a loss function. The trees are built in a sequential manner, where each subsequent tree focuses on correcting the mistakes of the previous trees. In conclusion, the development of decision trees from the ID3 algorithm to the present has significantly influenced the field of artificial intelligence and machine learning. Starting with the information gain-based approach of ID3, subsequent algorithms such as C4.5, CART, and ensemble methods like random forest and gradient boosting have improved decision tree learning in terms of handling continuous attributes, handling missing values, reducing overfitting, and achieving higher accuracy. These advancements have made decision trees one of the most popular and widely used machine learning algorithms, known for their interpretability, versatility, and effectiveness across various domains.